Hello, welcome to the fourth week of course. This week we'll cover a bit of some odd topics. We're gonna first look into qualitative analysis, that is way less organized than what we have been looking at, and then we'll cover a miscellaneous of methods that might solve some equations. And we're gonna be looking more in depth in another video, but the general gist of this week is that it's an overview of methods that might be very useful in some situations, but they are not as straightforwardly classified as the methods we have seen until now. So up to now, we always started the lecture by stating which specific category of problems we could apply our tools to. This week is going to be more on the vague side. Sometimes you'll be able to apply these tools, and that's great. Sometimes you'll be able to apply these tools only struggling a bit, and sometimes it's honestly impossible to apply them as straightforwardly as I present them. So it's very much a bit more on the intuitive side than what we have seen up to now. So let's start with qualitative analysis. It means that we are just looking at the qualities that the solution has. Up to now, we have looked at finding the exact solution that solves our ODE system or our ODE problem. Here we're going to be looking at what are the properties that our solution has, even though we might not be able to actually compute it. So it's a bit of a different approach than what we have been looking at previously. Let's go a bit more in depth. We can now solve first order ODEs that we have covered in the first week, first order constant coefficient systems of ODEs, higher order non-homogeneous linear ODEs with the Laplace method. But a lot is still not answered, in particular non-ODEs. Non-linear ODEs. And the uncomfortable statement is that there is no one-size-fits-all. But there are still quite a lot of things that we can do to solve nonlinear ODEs. This week we're going to look at how to use physical understanding to solve our problems. So let's look at this second-order nonlinear ODE. X second plus second derivative of x plus x to the third equal to 0. X to the third is one term that is nonlinear in this situation. We introduce the term m equal to 1. Why? Just because we wanted to get closer to the physical understanding. And we see that we can write the second derivative of x as some term that we can call the forcing. So we restructure the initial ODE into the form ma equal to f. And we can take a next step. We can say that f is the derivative of a potential, and we can expressly compute the potential in this case. So this, in this case, is a sum of x squared plus x to the fourth. We know how these things look. So we can understand the solution of our full example by looking at the potential v and understanding that a particle on this potential would travel down this parabola-shaped potential and oscillate around the zero. We don't have a precise formula about this oscillation, but we can still understand it. We can be a bit more precise, and we can also rewrite our problem by multiplying each side by x prime, noticing that on the left-hand side we have the derivative of half the mass times x prime multiplied by itself, and on the right-hand side we have the full derivative with respect to the time of the potential written as a function of x. So we can even rewrite our initial equation as a full derivative of a time of something being equal to 0, that is conservation of energy. So again, we don't have a full understanding of the analytical solution of this problem, but we know how the potential looks like, and that gives us an understanding. We know that it satisfies conservation of energy equation, so we can say that it has a periodic orbit. So we can merge this information, the first one telling us that from any point on the potential the particle will tend to zero, the second information saying that the energy is maintained, so anything that was velocity at some point would transform in height and the other way around. So we can state clearly that the solution oscillates around x equal to 0, and each solution is a periodic orbit. That means it comes back to exactly the same situation it started with. This we can say without ever solving the full problem. The take-home message is that if you need an understanding of the solution, you might find it by studying the physical model that is behind the ODE, or a physical understanding of the ODE that you're studying.